this was August 2004, and that produced one peak, one initial Meteotsunami with a wave height of 0.30 centimeters, and then a secondary peak that was observed after the landfall. Okay, so then what we did was we tried to analyze statistically how was the time variation of the number of occurrence, the number of events that we would see in the whole time series. So here what we have in the x-axis are years. So what we see is that in both stations, in Naples and in Clearwater Beach, there is some yearly variability, but we can also identify a longer variability in the signal, and especially in Clearwater Beach. So there is a variation that is like about 4 years or something like that. If we look at the maximum wave energy, this is the monthly maximum wave energy, we can see the same, more or less, that we have like peaks, and those peaks, they repeat every 4-5 years. And these two parameters, to treat them statistically, it was not very easy because this is number of events. It's a discrete parameter, so it's a statistical treatment. It's not that easy, and it can get a little bit complex. This represents the maximum monthly Meteotsunami height. So it represents the tail, the extremes of the Meteotsunami. So we wanted to use a parameter that would represent a little bit more the mean behavior. So we defined another parameter that would represent the Meteotsunami activity, that is the monthly integrated Meteotsunami height. And this merges the information of the frequency or the occurrence, but also the intensity. So what we can see here is that, again, what we see is basically a semi-annual and annual variability in both stations, but we can also identify a longer trend in the signal. So basically, to analyze a little bit better how was the variability of this signal and which were those periods in which we had a higher variability, we computed the power wavelet spectrum of the Meteotsunami activity signal, and we saw that there were peaks, common peaks in both signals located in the yearly variability, semi-annual variability. We had a peak in between 1998 and 1999, another peak in 2005 in both stations, and another peak in 2010. And then we have another persistent band of variability, basically in longer periods. This is in periods of 3 years, 4 years, 5 years. So the question here was, what is creating all this variability? What is the mechanism by which we get this variability? So I'm not a meteorologist, and this is the problem when we analyze Meteotsunamis. We have to read a lot of papers about what is going on in the atmosphere because it's the main forcing that drives the Meteotsunamis. But basically what I read was that the storminess level in this part of the Gulf of Mexico, it's very influenced by El Niño, La Niña oscillations, and NOW oscillations, the NOW index. So basically we took these two indexes, the Niño index and the NOW index, again make their power, the wavelets, we computed the wavelets, that is what we are seeing in these two pictures. And I wanted to point out that basically the years between 1997 and 1999, that period corresponded to the strongest El Niño period of all these time series. There was another peak on El Niño, or moderate El Niño was in this case in 2010. And then in 2005, there was an extreme activity of hurricanes, tropical storms in the Gulf of Mexico, okay? So basically, I think this is what it is creating, these peaks in the Meteotsunami activity in the Gulf of Mexico. Basically that El Niño drove more storminess in the dry season, and that produces a higher probability of having meteotsunamis and more extreme meteotsunamis in the area. And of course, like having more hurricanes, it's going to increase the number of meteotsunamis in this area as well. So to check if that hypothesis was true or not, we computed the cross wavelet between those indexes and the meteotsunami activity in here, for example, what I'm showing it in Naples. We also computed the coherences, but I'm not showing it here. So here, for me, the most important thing is what happens in the highest periods. We see in both cases, both with now, this is with NIño, with the NIño index and with the now index, we see a persistent, significant power of both signals in these long periods between 3 and 4 years. And in this case, what the arrows are showing is which is the phase between the time series. So if the arrow is looking in this direction, basically what it means is that there are in phase. That means that a positive El Niño will create an increase in the activity of the meteotsunami level in this area. And the now would act in the opposite direction. We would need a negative now to produce an increase of the meteotsunami activity. So how El Niño, for example, influences the meteotsunami generation and their intensity could be explained because it seems that El Niño, La Niña periods, what they affect is the storm track of the dry season storms in this area. So during El Niño, this storm track is located southwards, as we can see in this image over here. And during La Niña, they are located, the mean storm track is located northwards. So basically having a southern track, what it does is that the northern Gulf of Mexico is exposed to more extratropical storms, and basically also what it happens is that the temperature in the Gulf of Mexico is higher, so the interaction between the cold air masses driven by these extratropical storms and the warmer waters in the Gulf of Mexico, it's more intense, and they create more convection and bigger fluctuations in the atmospheric pressure. And I wanted to finish with this image. This is the sea surface temperature anomalies, the global sea surface temperature anomalies taken this year in August, and it seems that we are in an El Niño year, so we will see what happens in the winter, and we will see if we see this increase in the activity of meteotsunamis in all this area of the northeastern Gulf of Mexico. So I hope I had shown you that these waves are more frequent than what we think, and yeah, if you have any questions, I will be happy to answer.